Are we good?
Yep.
Okay, great. Welcome everyone to Wormhole Day. We're happy to kick it off with Vijay Balasubramanian from Penn, who will tell us about the origin of black hole entropy. Take it away.
Great. Well, thank you very much for inviting me to this workshop, and lots of fun, very interesting discussion so far. It's also my first time in Saclay, so I'm been actually really enjoying the visit. Perfect weather and everything. Great. So today I will make some comments on the origin of black hole entropy, and everything I'm saying is based on two papers with Albion Lawrence, Javier Magan, and Martin Sasieta. A special praise for Javier and Martin, from whom I basically learned everything that I'm going to discuss in this talk. So they're really wonderful people. And Martin's a postdoc at Brandeis, and Javier is a new assistant professor at Bariloche in Argentina. Great. So let's start with the problem that we want to think about. So I'm going to talk a little bit about the puzzle of black hole entropy. So let me remind you what that puzzle is. So in 1973, Bekenstein, Bardeen, Carter, and Hawking proposed that black holes carry an entropy which is equal to area times the speed of light cubed divided by 4 g Newton h bar. We're going to set h bar and c to 1. And the really remarkable thing about their paper, about their papers, was that this formula appears to be completely universal. Right? So it applies to black holes of any mass, of any angular momentum, of any charge, and in any space-time dimension. It's just a fact, apparently, if you believe their arguments. And what were their arguments? Well, principally, their arguments were kind of Gedanken experiments. And they imagined a family of black hole solutions and asked how those black hole solutions change when matter passes through the horizon. And so they observed that if you have a certain amount of mass, delta m, pass through the horizon, then the area change, delta A, is related to delta m. So delta m is kappa delta A, where kappa is a thing called the surface gravity and is constant over the horizon. And what's more, in classical processes, delta A, the change in area, is always non-decreasing. Now, clearly, these things are in formal analogy to the laws of thermodynamics, of which these authors observed. And then they also said, well, don't take the analogy too seriously, because if this analogy were a good one, then black holes radiate with a temperature kappa, and everybody knows that they don't. So, well, a couple of years later, Hawking comes by and considers quantum mechanics in the background of a black hole. And then you can imagine processes like pair production just outside the horizon. One member of the pair falls in, one member of the pair falls out because of the kookiness of the directions of time near the horizon versus outside. The one that goes in effectively has negative energy relative to the time like killing vector at infinity. Net effect, the black hole radiates thermally with the temperature kappa. Wow, so the analogy looks perfect. Okay. So it's actually useful to consider a more formal argument than this kind of reasoning by analogy, which is what we talked about just before. So to think about that more formal argument, also given by Hawking and Gibbons in 1978, it's useful first to back off from gravity and think about quantum field theory and how we would think about entropy in quantum field theory. So consider a quantum field theory with some fields phi and an action I. So a way of accessing the entropy of a quantum field theory is to consider the path integral in Euclidean signature. So we take t to I times tau and make time periodic. Tau goes to tau plus beta, is identified with tau plus beta. The path integral with those boundary conditions, Euclidean path integral with those boundary conditions, computes the partition function. Namely, that path integral is computing z, the partition sum, which is the trace of e to the minus beta h, h being the Hamiltonian, because this object is computed by this object, which is the path integral with periodic boundary conditions across time of e to the minus 1 over h bar, it's Euclidean, of the integral of the action. Now, in general, these kinds of path integrals are very hard to do. So at least when h bar is small, we are wont to do them via the saddle point approximation. And then we should, of course, discuss how good is the approximation, etc. But in the saddle point approximation, you basically say that this thing is controlled by its critical points. So you compute the saddle points, and you write down this is approximately e to the minus beta times the saddle point action. Right? Of course, there are corrections. You can compute the determinant around the saddle point. You can add more saddle. You can do. There's a series of corrections. But the leading order, you're hoping it's this. In this analogy, well, strictly speaking, there should be a sum, by the way, here, right? If there's multiple saddle points, you should add up the saddle points. Anyhow, we now identify I here as the free energy, because Z is equal to e to the minus beta free energy, and therefore the entropy, according to your standard StatMech textbook, is beta dd beta minus 1 acting on the free energy, and you can calculate that. And what do you know? You find exactly the same, and that's the entropy. So now let's do this in gravity. And I'm repeating all of this, even though much of the audience is very familiar with this, because I'm going to kind of use these tricks again and again and again. So I want to be completely clear on what we propose to do. We're going to apply this to gravity. We take t to I tau. We identify tau to tau plus beta. We're going to consider theories of gravity. So they're going to have, the Ricci scalar, some cosmological constant, extrinsic curvature terms on the boundary to make the equations of motion well-defined, because, the bulk action has two derivatives, not one. So you need these terms to get good equations of motion, good Euler-Lagrange variations. And when possible, we may add counter terms, for example, anti-de Sitter space, to make the action finite. Otherwise, you've got to regularize, subtract some infinities and so on. So according to the previous prescription, we want to do the path integral with this action. Well, does that path integral even exist? Well, I don't know, gravity, that's a complicated issue. It may exist in the sense of having some ultraviolet completion in some theory like string theory, but nevertheless, even if it had some ultraviolet completion like that, if you try to do the path integral, there's certainly an effective sector, a low energy sector that involves gravity, and the saddle points are going to involve the equations of motion for that thing. So we're going to approximate this with saddle point. So what are the saddle points if you do the path integral for this? Strictly speaking, completed into string theory. Well, the saddle points look like this. This is the metric for them. They're basically Euclidean black holes. So what are they like? So these geometries have the form of what's often called a cigar. So the geometry looks like this. Euclidean time is going this way. It's periodically identified. And if you look at it from the right, which is what I will mostly do during this talk, it looks like a disk. And the origin here is the Euclidean horizon. The horizon is a causal construct. So in Euclidean time, you're not going to have the interior sitting around because there are no null curves. So this point here plays a role of the origin when you analytically continue back to Lorentzian signature. It's this point that will bifurcate into producing the horizon. Anyhow, in this interpretation, I should take the saddle point action, compute beta d beta minus 1 of the Euclidean action, compute it on the saddle point, and what do you get? You get area over 4g Newton. So this was Gibbons and Hawking's formal argument for why you should consider that black holes have this entropy proportional to the area. So the pictures I'm drawing are basically appropriate to vanishing and negative cosmological constant, flat and ADS space, and I'm going to basically stick to that. Actually, mostly I'm going to talk about ADS space, because then we have the boundary dual to confirm for us that the things we're doing are valid, and I know what I'm doing. But I will tell you that the calculations done in the bulk as such are the same, essentially, in flat space. So the argument done as a bulk argument would go through in flat space. I'll tell you about that later. So positive cosmological constant, which we may have in our world, is a bit different since the Euclidean geometry has no boundary, and I won't really have anything useful to say about that today. Okay. So if something has an entropy, it behooves us to ask, following Gibbs and Boltzmann, what is the origin of the entropy? Now, Gibbs and Boltzmann said that if you have a system that acts entropic, thermodynamically entropic, you should think about the entropy as the logarithm of the number of microstates consistent with the macroscopic parameters. So another way of saying this, if you kick a system, right, well, if you're a big chunky thing, part of what controls how you interact with it is the phase space of microscopic stuff that exists, like following from kind of observations Emil was making yesterday. And that phase space, the size of that phase space, of accessible phase space, the logarithm of that is the entropy, is the thing that acts like the entropy. So what approaches have there been to answering the question of the origin of the entropy? Well, so one classic approach is the precise count of the microstates of certain black holes in string theory, that's Strominger and Vafa. In fact, this is the paper, reading this paper is what really brought me into string theory as a field. Beautiful paper. Why isn't the problem solved? Because in order to apply these approaches, you need lots of special conditions. First of all, this is a supersymmetric black hole, 32 supercharges broken to 4, and it's that allows these authors to take the finite Newton constant you need to have a horizon, make it really teeny tiny, so it's no longer like I have finite horizon, but you keep the degeneracy fixed, and then you can do some exact counting techniques in using supersymmetry. You also need all the paraphernalia, of course, of string theory, extra dimensions, branes, multiple electric and magnetic charges, and in the world around us, you don't really see many of those. In this sense, this argument feels specific to these sets of scenarios. absolutely gorgeous, but specific, and doesn't have the character of universality of that formula of Gibbon, the Bekenstein-Hawking formula that I talked about before. Another beautiful approach to the same question has been the fuzzball approach, which I think the members of this audience are especially famous practitioners of. So this, I understand this approach as being basically the finite G-Newton version of the kinds of things that Strominger and Wafel were doing. People are trying to find, in some large extended sense, right? When G-Newton is finite, what are these silly microstates, right? What do the microstates at 0 Newton constant flow to when you have finite Newton constant? So you know well that another point in the fuzzball program is that if you truly have a microstate, well, there shouldn't be a horizon, should there? Because there isn't really an entropy. The entropy is 0. So the idea is somehow the detailed configuration doesn't have a horizon. Of course, you may effectively have a horizon if you examine it with coarse observables, but in detail, right? It's like the gas in this room. There is a state or a configuration it's in. It doesn't have a horizon. In that sense, at least that's the view taken in the fuzzball program. And by and large, in order to be able to find these solutions, which are really tour de force calculations in gravity, you need supersymmetry, extra dimensions, all kinds of things for stability and control, with specific exceptions. There are examples where you can find these kinds of configurations without supersymmetry and without some of these things. But in general, you need that. And so once again, this feels not universal in that sense, and not like the black holes we see around us from collapse. And also, this approach is definitely harder than this approach, and not enough states have been identified in general, in most cases, to explain the entropy. That doesn't mean that they aren't there, right? It just means they have. This is a hard program to follow. Okay, there are other approaches too that people have studied. So for example, people have considered that the entropy of black holes is supposed to be given by entanglement between interior and exterior degrees of freedom. And I learned about this first from Holsey, Larson, Wilczek, and then Susskind, Uglum, etc. And these kinds of approaches face the challenge that they diverge in quantum field theory. It's not clear how to do the computation in string theory, etc. Raghu has a question. I had not expected a question from you, Raghu. I'd expected a question from Samir. Okay.
So about the
Is the microphone on? Yeah. Good.
in the counting solutions versus computing a number for the entropy, I mean there's a basic thing that typically the number of classical solutions can be infinite, and then you need some kind of geometric quantization or something to get the precise entropy. So is that so it's not, am I right that it's not just about constructing sort of some number of solutions, but then you also have to do
So I mean, that's of course a question that should be addressed to the community in this audience. But of course that's the case, right? I mean, so we know well, for example, if you look at classical gases, you know that to get the correct answer for the entropy of a free gas of free particles, you need to have the quantization of phase space with an h-bar. And indeed, you could have predicted, well, you could have known that quantum mechanics had to happen already by looking at the thermodynamics of free gases before the advent of quantum mechanics by requiring that quantization. So yeah, of course. And I think that's understood implicitly as part of the fuzzball program. But Samir now just have a comment.
No, I just want to add a comment to that. Slava Rychkov actually did that some years ago. He took the two-charge family of states, and then he did the semi-classical quantization using the Witten-Chernkovich bracket, and he got the exact number.
Yeah. And doing that in general for general fuzzball solutions, challenging problem again. But indeed, Rychkov's calculation is the primordial version.
Just another comment. There was also some beautiful paper by Jan de Boer and Massimo and Schuk doing semi-class quantization of a limited family of. I missed an author on that paper. Limited family of 3 charge problems too. So, and it leads to some really interesting physics where supergravity approximations apply, and yet the phase space volumes are very, very small for ridiculously big geometry.
Yeah, no, absolutely. That's a beautiful paper. I should have mentioned it because we subsequently used some of that stuff in some review we wrote. Yeah, okay. Good. Okay, so I'd like to pose the puzzle today in a somewhat different way, right? Rather than talking about, oh, wow, where are these states? There are too few of them, it's hard to find. There's a certain sense in which actually there are plenty of states and there's way too many of them. And the way of phrasing that is like this. So suppose this is the black hole horizon. And I'm going to imagine a thing that I'm going to call a semi-classical microstate as a state that's well described, a state inside the microstate inside the black hole that's kind of well described in effective field theory coupled in matter coupled with in the effective field theory of matter inside the black hole with a fixed exterior geometry. So I'm going to imagine that there are many different possible states I may try to insert here, right? Microstates, which have the same exterior geometry. So our idea of what's a microstate is going to be outside the horizon, it's the same. Exterior observers see the same thing. That's the macroscopic variable we keep fixed, and we can have other things inside. So so suppose you try to put tennis balls here, right? There's actually space enough to put vastly more tennis balls inside the black hole than e to the area over 4g Newton. So at some level, it's clear that there's sort of vastly too many states, not too few, vastly too many states, because surely I can put tennis balls inside the black hole. So this is basically sort of Wheeler's kind of idea of the bag of gold, that the space inside the black hole is this big thing. You can stuff lots of stuff in it. It's like a big sort of bag of gold. And one would say that this phrasing it this way sort of reverses our problem. It says that there are too many states naively in the effective field theory. So we might ask the question that way. I have lots of these things. Now, how do you figure out that they actually span a Hilbert space of the right dimension? I do have a hope of finishing this talk. So it's not all.
It is actually related to the previous comment now. So this seems like a classical statement that you have too many.
Yeah, of course. I think you should let me continue with my talk, because obviously what I'm going to try to do is to quantize this, right? Yes. Okay. So I'm going to discuss our approach and results, right? So that's the point of my talk, right? Okay. As you know. So okay, to continue. So what's our goal going to be? So the idea in this talk is that we don't actually need to find a specific, cleverly designed family of microstates, like the clever things that Strominger and Waffe used, or the clever things that the fuzzball community tries to design. Rather, the idea is that perhaps all we need to do is we need to take any old crazy family of microstates that we can calculate with. Right? It doesn't really matter what they are, so long as they can show that they span a Hilbert space of the correct dimension, and what's more, that they are, with a reasonable argument, a complete basis of states. And then I've solved the problem in this way, perhaps not completely satisfyingly, because I would like to know what the typical states actually look like in some proper microscopic way, but still, I will have solved the problem in this way. So that's going to be the idea. So our approach is going to be, we're first going to construct an infinite family of well-controlled, by well-controlled I mean semi-classically well-controlled microstates. Right? And we can discuss to what degree you agree with that and to what degree these are microstates and exactly what I mean by that. We'll talk about that in a minute. From these, I'm going to construct the grand matrix of overlaps between these states. I'm going to construct these things as quantum states, even though they have good semi-classical descriptions, right? They're still quantum states. I'll construct the overlaps between these states. I'm going to construct a matrix of overlaps. Then I'm going to compute the rank of this matrix. And the rank of the matrix is the Hilbert space dimension. And so I'll tell you the results, because given Raghu's questions, I'm probably not going to finish this talk. So the results are that, first of all, we're going to show in this way that the entropy measured as the dimension of the Hilbert space of these states is exactly area over 4g Newton. I'm probably not going to get to this. I have one slide each of these things. So I'm also going to argue to you that the extension to flat space and collapsing geometries can be done of the calculation. So you can do this in flat space. And thirdly, there's an interesting side result here, that long wormholes are superpositions of short wormholes, which is going to suggest that area is not a linear operator in quantum gravity. Right? And really suggests that we should be really thinking about what makes a geometry reliably classical kind of carefully. Right? Because very big things can be superpositions of very small things. And so there's something very unusual about that. Volume's not a linear operator. Okay, yeah, volume's not a linear operator. Okay, so let me start with this notion of a semi-classically well-controlled microstate. So I'm going to try to keep, since I want to discuss technical details in this talk, I'm going to try to keep things as well-controlled as possible. So I'm going to start, for simplicity, with time reflection symmetric states in asymptotically anti-de Sitter space. We can do similarly in flat space, But if I have the power of the ADS-CFT correspondence sitting behind me, there are many things that I can say as also statements in the dual field theory, and therefore we have more control and we can rely on what we're going to say. We're going to consider eternal black holes for this reason, because we want to talk about, I don't want to talk about collapse geometries. And in this case, here's the Penrose diagram of the ADS eternal black hole. Here's the singularity, here's the horizon, and here's the boundary of space. As you all know well, if I slice this geometry over here, that looks, on an equal time slice, this looks like a wormhole. And these are basically Einstein-Rosen bridges. So what are the kind of states I'm going to construct? I'm going to construct states in which in the inside, behind the horizon, there is a dust ball, shall we call it, a shell of matter, basically propagating inside. This thing will have a trajectory controlled by its equation of motion and the Israel junction conditions and so on, and sort of emerges from the past and goes into the future. And geometrically, this thing is going to look like a long wormhole with a shell of matter behind the horizon. But every such thing that we'll construct is going to have exactly the same geometry outside the horizon. So in some understanding of what is a microstate, these are microstates because they're the same outside, they're just different inside. Okay. And so I'm going to think about these as highly atypical states, microstates of the black hole, which happen to be under semi-classical control. Right? We've written things down that happen to be under semi-classical control. How can we construct such states? So I'm going to remind myself of how to do this by using quantum field theory and the standard ADS-CFT dictionary. So remember that if I take this eternal black hole, then in the vacuum, the state it's related to is a thermal field double state in the product of two Hilbert spaces HL cross HR. And the thermal field double state in the CFT, in the dual CFT, is given by taking energy eigenstates on the left and right, thermally weighting them, and dividing by something involving the partition sum. Suppose I told you, please prepare this state for me in some nice way using a path integral. What would you do? Well, we would use the Euclidean path integral. We would first make the whole thing Euclidean. And so the boundary of the ADS space in the Euclidean ADS space is going to look like a cylinder. This is like, there's the cylinder. This is like the outside part of that disk. You remember we were talking about the disk earlier of the Euclidean black hole. This is the boundary of that. And the circle is the circle on the boundary of ADS. It's actually the sphere on the boundary of ADS, right, which I'm sort of suppressing in most of these pictures. So here's the sphere on the boundary of ADS. That's where the CFT lives. You start with this picture, and you evolve by beta over 2 in both directions, the CFT on the boundary, and that will prepare for you the thermal field double state. This is the standard preparation of a thermal field double state in a CFT. So what's the bulk dual of this algorithm? The bulk dual is, well, fill the thing in. So you're supposed to fill the thing in. If you fill the thing in, this is the geometry of the Euclidean black hole. You're supposed to evolve the gravitational theory forward in time, slice it at t equals 0, and then match it on to, and if you want to then get the Lorentzian state evolution after that, you match on to the Lorentzian geometry on top of that. The Lorentzian geometry is the Lorentzian black hole, and the horizon bifurcates out from this, from the Euclidean horizon. So that is also the standard prescription in ADS-CFT for how you're supposed to get the thermal field double state in the bulk also. Okay, so this is standard. So now what would we like to do? We'd like to make a different state, right? One of these kinds of, quote, microstates. So in the field theory, the kind of thing we can do is we can apply an operator over here and then evolve the state forward in both directions. So I want to make a dust ball. And so to make a dust ball, we will make a little cloud of operators over here, right? Spherically symmetric, nicely, smoothly organized. And then we'll propagate it this way by some temperature, by some time, beta L over 2 and beta R over 2. I've put a tilde here for a reason that you'll see in a minute. So we don't quite want this to be the temperature of the black hole. We want to be slightly different from that. I'll tell you why in a minute. And that will produce a state of this form. And these things, these are what I'll call the preparation temperatures. And I'm going to tell you that you can pick those preparation temperatures so that the total energy, mass / temperature of the geometry outside the black hole is held fixed, even though you threw the shell inside. So that's what we're going to try to do. So you can choose O to have a semi-classical dual. Right? So a good description, a reasonable semi-classical description. So to create a basically spherical cloud of dust particles. For example, if phi is an operator of dimension delta phi in the field theory, then the operator O we're considering is like a product of these phi's at different locations. And if you pick delta of order 1 and n, the number of operators you're going to apply to be of order 1 over g Newton, then these are big, chunky, heavy, shells of matter. Not ridiculous shells of matter, but shells of matter of the kind that have a back reaction and affect the geometry and things of this kind. Lest you worry that there's something non-kosher about this, this has been done for more than a decade, right? There are papers, for example, nice papers by Tom Hartman and his various collaborators, putting in shells of dust like this from infinity, dropping them in, things like this. And they reproduce beautifully the results of calculations like correlation functions in thermalizing states. So that's been done. They match calculations that we did using Vijay metrics and things like this. So there's every reason to believe that these things are good. What's more, you can place these particles in such a manner that you're not getting them closer than the Planck distance. You can control this, is what I'm trying to say. Right? So you can have a well-controlled kind of state of this kind. Samir, you have a question? Yeah.
So yeah, I'm sorry I might have asked you this before also when I had heard about your work, but I just wanted to mention, if you go to the slide even before that, right, so I've always had a difficulty with this, which may again come up in later steps, that when you actually make the thing by the picture on the left, then the two circles you get are actually not touching each other by any Hamiltonian interaction, because there is no Hamiltonian vertex between the rightmost point of the left circle and the leftmost point of the right circle, while the picture on the right actually assumes that if you take the right segment, the left segment, there's also a link in between, which allows a particle to go from the left side to the right side.
So certainly not here, right? So certainly once you come into the Lorentzian part here, this is causally disconnected.
No, so what I'm saying is you can cross the midpoint. So if you just take a line on the right side in the Lorentzian region, you can, in the Lorentzian side on the right, if you draw a line, it can cross the vertical line in the middle. So a line from in the right and the line in the left can meet in the future region.
In the middle here,
right. And if you actually take the state which comes from two disconnected pieces like that, that's not possible.
So I don't think I'm going to solve this problem for you right now.
No, I understand.
Because
I'm not going to hold you up.
And as you also know, that this particular preparation of the state and the analysis of what it means that these two things are disjoint theories that are entangled and nevertheless have an interior, this is a long story in the ADS-CFT correspondence.
Absolutely.
So I would much rather not have to defend that here, because there's a long body of work showing that that analogy or that equivalence works well.
So I'm saying that I actually think that it's an incorrect equivalence. I just want to say that I think all the troubles with this part of the story of the field start because this is incorrect, but we can discuss that later.
Okay, let's discuss that. Yeah. So that is not a view shared by, I would say, like what, 99% of the field.
Absolutely.
But that's okay.
That's why it's so important.
Let's discuss this offline, because then if we try to sort that out, I would not get through the rest of this.
I also have a question. You said that people have formed such geometries by collapsing some form of distance.
No, not these particular geometries, but there are. So you know how you can make a Vijay shell? Let's do a gravity calculation first. Drop a shell of matter in from infinity. There's the Vijay metric that describes it, and then you can compute correlation functions and entanglement entropies in this background and see them thermalize. The analogous calculation, so that was a paper by myself, Ben Krabs, Cast of Thousands, Jan de Boer, Masaki Shigemori, bunch of people, Alice Bernamonte. Then there's an analogous calculation that was later done by Tom Hartman, Alice Bernamonte, Federico Galli, a couple of others, okay. Whose names I'm forgetting, unfortunately. And what they did is they said, let's just make the shell of matter for real in ADS-CFT by inserting a spherical cloud of operators in CFT. It's basically this thing. But we're not going to do this, what they did, because they dropped the shell in from infinity. We don't want to drop it from infinity. I'll tell you exactly what we'll do in a minute. Anyway, they dropped the shell in from infinity, and then they use heavy, light techniques for computing correlation functions in different kinds of states, right? They make heavy states and then compute correlation functions of these operators in those states. And that calculation winds up reproducing precisely the results that were produced in gravity. So that's a reason to believe that this kind of construction is valid.
Okay, and when they drop this, they form a black hole in the interior, or?
I can't remember exactly what their scenario was. In their scenario, they might have had a black hole to start with, and they were trying to make it, or maybe there was no black hole, and they make the black hole. I can't remember exactly what the scenario was.
Okay, thank you.
But if you look around 10, 12 years ago, 10 years ago, roughly, you'll find their paper.
Okay, thank you.
And ours. Okay, so right. So now I want to continue with the gravitational description. of this process. So in the gravitational description, modulo Samir's doubt, is that, well, what do I do? This is the bulk. And I insert a shell of matter over here in the past. Okay, this is the Euclidean section, not Lorentzian. So that's just like having the shell inserted here. And we're supposed to fill in the bulk geometry and time evolve this way and this way. So if you do this and try to compute the solution to the equation of motion, basically the saddle point. So strictly speaking, what you want to do is insert this boundary condition and do the path integral to get the wave functional over states of the universe at later times. The saddle points of those things are solutions to the equations of motion. What are they? Well, they're going to look like this. Here's the, this disk in the past. Here I'm suppressing the circle over here, right? This disk, like that. This boundary. And there's a shell of matter that will propagate in this way. So it's basically general relativity plus a shell of dust is what you're trying to solve the equations for. It'll have Israel junction conditions, right? So there's some energy, stress energy on the shell given by there's some local inertial mass, density, and so on and so forth on the shell, and some velocity vectors. And well, this thing will have some mass. It'll drop in. And there'll be some geometry on the left and some geometry on the right, spliced together by the Israel junction conditions. So what does that look like? At the end of the day, you have a solution that's going to wind up, well, the metric looks just like the metric of the Euclidean black hole, both on the left and on the right. I'll tell you how to match them in a minute. So here are the general metric functions, and the trajectory of the shell is controlled by some equation of motion involving the radius of the shell moving in some effective potential. This is kind of elementary calculations in general relativity that it's just a matter of sitting down and doing it. It turns out that there are infinitely many solutions of this kind with exactly the same exterior. You can make these shells much heavier. You can put multiple shells. You can do many different things like this. And you can construct them in such a manner that the exterior geometry is completely unchanged. And you might think that perhaps I should think about this, therefore, as some infinite family of putative microstates. Why? Because the exterior geometry is fixed, and I've got many different geometries behind this horizon. So in order to make sure that they're behind the horizon, there are actually some constraints. Yeah. No. Let me explain the construction. The Gauss law does not tell you here that you're not violating Gauss law. This is behind the horizon. You're not violating Gauss's law.
No, that's my point. I mean, outside the geometry is completely determined by the mass. If it's spherically symmetric, because you're assuming spherical symmetry.
Yes.
You're not describing rotating black holes or whatever.
Yeah.
So.
All right, fine. Usually when I give this talk, if you're happy with it, cool. Let's just move on, right? Usually when I talk about this, somebody says, "But you put a shell of some mass behind the horizon. How come it didn't change the mass?" I'm trying to explain that it doesn't. If you're good with it, let's just move on. You don't even have to listen to the next slide.
But I mean, that's a constraint. I mean, you put this constraint on the mass of the system.
I'm going to put the constraint now, right? So this because you could insert the shell in a manner that you change the exterior mass, or you could insert the shell in a manner that didn't change the exterior mass. So let me explain this in a second. But if you're good with it, just ignore the slide, right? So you want to insert the shell, and on the right-hand side, I want the shell to be kind of behind the horizon, okay? So this is the Euclidean horizon. So this is the right black hole, if you like. In that, you remember I was saying that the right black hole, the left black hole. This is the right black hole. And here's the Euclidean horizon. I want the shell to be on one side of the Euclidean horizon because I want to splice it to the left. The shell should be to the left of that. I also want the entire geometry to be such that the inverse temperature is the same, right? So that the mass remains unchanged. So I require that this thing be a section of a circle that has a circumference beta r. But the shell is going to adopt some trajectory so that it'll elapse some Euclidean time delta r. So the constraint then we have to get this to work out correctly is this circumference plus this circumference, that's the preparation temperature as we call it, plus the elapsed time of the shell must equal beta r. And if you impose this condition, the exterior geometry will be unchanged. But there's a constraint you've got to impose on this. So you do that, and you get you do that on the left also, and then you'll get a picture like this. The shell moves this way, and the geometries on the right and the left both have Euclidean horizons in two locations like that. And then if you were to splice this onto a Lorentzian geometry afterwards, cutting at t equals 0, it would look like a shell that's passed behind the horizon with the horizon on the two sides. That's our construction.
Could you say again how the two dots came about?
Hmm,
Because
yeah.
in the top picture you have one.
Yeah. So you have so notice here that this is a Euclidean black hole geometry. And notice here, this is a Euclidean black hole geometry. Let me regard the solution from just this side for the moment. I want to just talk about this part of the geometry. So what you do is, okay, that part of the geometry is a section or a piece of a Euclidean black hole. Here is that Euclidean black hole. It's this circle. I require it to have whatever temperature is appropriate to having the correct mass. And then I fix it, the parameters, in such a manner that this passes to one side of it. But I'm going to do the same thing on the other side, except the shell will pass to the right of it. So that's the geometry, and this is what you get. You good? Okay. Okay, just by the by, this is just, I'm going to say this in one slide. Asymptotically flat, one-sided black holes work similarly. You can similarly drop shells behind, and then the way things will work is that you'll get flat space behind the shell. This is r equals 0, this is the origin, and then you'll get the black hole geometry on this side. And if you take an equal time slice, this will look like, basically a throat coming into the horizon. There's inside, there's some shell, and there's a smooth cap. Right? This is one of these smooth cap geometries that looks a little bit like a bag of gold. So, okay, so you can do, so everything that I do in the bulk of gravity, you can do perfectly well in flat space and with one side. The reason I'm not doing that in this talk is, of course, we don't have a dual CFT. So I can't quite do all the, oh, yes, you should believe me, because I could do a dual calculation in that way. Okay. So let me summarize where we are. So we have made a bunch of states, which I'm going to call psi m, which consist of shells with many different masses. I want them all to be semi-classical controlled. So I'm going to take the masses to be of order 1 over g Newton, right? 1 times 1 over g Newton, 2 times 1 over g Newton, etc. And I can essentially make an infinite number of such shells, states. In fact, you can make states with 2 shells, 4 shells, 16 shells, whatever number of shells you want. There's really an infinite number of such things, which would seem a priori to challenge in a more pointed way than my tennis ball analogy, right? At this sort of classical level, it would appear to challenge the view that you should think about the entropy of the system as area over 4 g Newton, because there's many more states with the same macroscopic description. Okay, so one caveat that I would like to add is we have described semi-classical geometries, classical geometries actually. And of course, if you took the dust shell that we've talked about and moved the dust particles by tiny Planck scale amounts, you're going to get the same description. So the same classical description applies to many things that differ by tiny Planck scale, string scale details. So we're really thinking here that amongst those things that have the same classical description in that way, we're going to pick one state as the representative, right? And I'll tell you more about how we think about that ensemble of states that may have the same classical description in a little bit. So you should think about the shell that we're talking about as a kind of slightly coarsened gravitational description of one of these states, where you can move these dust particles around, maybe by tiny, tiny Planck scale amounts without a macroscopic effect. Okay, so that's the way I want to think about these shells, because these shells are going to be basically our trick for calculating the overlaps of the true underlying quantum states. It's a trick for doing that. Okay, and we'll tell you what that trick misses in a little bit. Okay.
Can I ask a question?
Yeah.
Even previously, when you described this solution, wasn't there a continuous family because you had this relation between the preparation temperature and the temperature that you want to fix? And so
yeah,
you have a range of,
so you can tune
a continuous
these,
range of choices.
Yeah, you can tune
Right.
these masses continuously if you want, in some classical sense. But if you're inserting dust particles, then there's some quantization to the deltas you can add from
Sure.
At that level, it's quantized, but its classical solutions, of course, they're continuous. Yeah, but here again, I'm going to lean on. I really want to think about these as being made by insertions of operators in the dual field theory, and then the conformal dimension of the operator controls it, especially if there's a gap.
Doesn't that partitioning of the beta R twiddle into the beta R and delta TR limit the number of options in terms of this Hilbert space?
Sure, there's still an infinite number, right? So,
but isn't there some quantization condition on these?
There, well, so we didn't find the quantization condition. So basically, here you stick in whatever stress energy tensor you want here,
right.
And that for us is given by saying you have n insertions in the boundary, but pick what you want, and then yeah, there's some relationship between the masses and how this thing moves and things like that. I can't remember exactly what the details are, but there wasn't any serious material constraint on that.
Okay, classically, I believe you that it was completely continual,
Yeah.
but isn't this some kind of? I would have expected some kind of quantization condition on the states.
On these temperatures. Well,
yeah.
I just stated one condition that comes about just because you have you insert shells with particular masses that are controlled by inserting some integer number of operators in the field theory. That's a quantization condition of one kind. I think you mean something more subtle, but I can't quote you one.
These Israel conditions, they introduce a stress tensor.
There is a stress. Yeah. Yeah, so there is a stress tensor. The Israel condition, so I would put it the other way. We have a stress tensor because we're really thinking about a shell of dust falling in. That has a stress, it has this one. It has this stress tensor. And so the Israel conditions have to be consistent with this. And this is a perfectly decent kind of, there's no negative energies, it's all perfectly decent inertial. It's really dust particles. Okay, so that's our states. And now we appear to have created possibly some problem for ourselves by having way too many states. So we'd like to understand, well, that can't be right, or maybe that can be right. Let's see.
What is the ADN mass of each microstate?
Exactly the same. Yes. No, that's the point of this construction. The point of and also Massimo's comment. The point of this construction is they have the same ADN. That's why we want to consider these microstates. The macroscopic parameters we keep fixed are, mass, charge, angular momentum, stuff like that. Geometry outside the horizon, in more detail, it's fixed. Okay, so, well, the out, of course, from saying you have way too many states is really these are supposed to be underlying quantum states. So we should compute their overlaps if we can, and see what we get for the rank of the Hilbert space, for the dimension of the Hilbert space. So I'm going to consider such dust ball states. Again, I remind you that each of these states is supposed to be, underlying it is one representative of the underlying states, dust states, which are going to have exactly the same classical description, because when you move the thing by Planck scales, the classical description looks the same, but we're thinking about dust states of this kind. Those are our microstates. So we're going to compute the Gram matrix of overlaps, so psi I, psi j, this matrix like this, and we're going to calculate the rank of G of this Gram matrix. To compute the rank of the Gram matrix, that's the dimension of the Hilbert space. To compute the Gram of the matrix, we're going to use an ancient linear algebra trick, well known, for example, in the random matrix community from decades and decades ago. What you do is you compute something called the trace of the resolvent of this matrix. And the trace of the resolvent is you take 1 over lambda I, lambda is going to be an eigenvalue, minus the matrix G, and you compute the trace of this thing. You can write that out in a power series in this way. And there are traces floating around in various places. And there's a theorem, a statement, that the eigenvalue density of the matrix G is the discontinuity across the real axis of R. So you compute the discontinuity across the real axis, and you can read out the eigenvalue density. And in particular, the number of 0 eigenvalues, that's what we, if you can compute that, so the density at 0, then the rank of the matrix is the dimension of the matrix minus the number of eigenvalues that vanish. So our goal, of course, is to take some very large bag of states with omega states in it. Omega is going to be huge, right? Much bigger than ETS or something, or maybe less than it, and then just simply compute the rank and see what we get. Right? That's going to be our goal. So let's do that. So I point out that this matrix contains sort of overlaps of this kind. So that means when we want to compute sort of trace of G to the n, the nth power, it's going to contain products of overlap, psi m, psi m prime, psi m, psi m prime, psi m prime, psi m. A notable point, because we're taking the trace of the object, is the first and last index are going to be the same. That's going to be kind of important, because that's why in various calculations we're able to get something that's not 0. Anyway, that's just a technical side point. So we're going to do all of these calculations by the Euclidean path integral. So let me explain what I want to mean by that. So according to our prescription for constructing the state, we make a state, let's say M, by inserting a dust shell there, doing the Euclidean path integral up to t equals 0 and slicing it, because that's what we said our state was. That's let's say the ket state. The Bra state is likewise produced by putting M prime at future infinity and propagating backward there. And then we need to sew at t equals 0 and integrate. And that's supposed to be the overlap between these states. Right? Now, that sets up the boundary conditions here and here. And then the rule on gravity is that they sum over all paths in the fields and geometries and topologies. You just do everything you can to connect these boundary conditions, and you sum them up. That's supposed to be the prescription that we would follow. So I'm going to try to do that. So if I'm doing this in gravity, psi m prime then is in some sense the sum over topologies of the integral, the sum over fields of the sum over metrics times e to this. Strictly speaking, there's sort of dots everywhere because strictly speaking, the path integral in gravity is only really well defined, presumably via some UV completion. But again, we're going to, just like Gibbons and Hawking, kind of approximate this with the semi-classical saddle points because that's the only thing we can do. Okay. So we're going to approximate this as a sum of saddle points in this way. And you know what the action was already. There's the gravity action, except now I need to chuck in also the action of any shells that I have in the game. That's the matter floating around in this system. That's our goal. Okay, so I'm doing semi-classical calculations. So because I'm doing semi-classical calculations, I'm going to put this line on top just to keep in track in the back of my head that I'm doing semi-classical calculations. I don't know how to do the true path integral, of course, in the microscopic gravity. So what does it look like? So the semi-classical approximation of this thing is going to look like you put this thing down, you move the shell down, and you're supposed to compute the overlap integral. So to leading order, that's a delta function, m prime. And there's going to be some tiny correction, which is exponentially suppressed in the mass difference, because you have a particle here, it can split into two particles. There's lots of particle physics processes. This is going to be suppressed and very, very heavily suppressed because you need order 1 over g Newton particles to interact, do crazy things and stuff like this in order to change one shell to the other. For our purposes, what we're going to do is we're going to take the masses m and m prime, and I'm going to declare that this piece of it, this correction, is under parametric control. I'm going to fiddle it so that the difference in the masses of these shells, and I've got an infinite number of them, is so large that whatever I get from this is going to be exponentially smaller than the other effects that I'm going to talk about. So I'm going to control these away in that manner. Okay, so that's the idea. So we treat this as 0 because it's under parametric control. And I'm going to make this go to 0 by making the mass differences between shells tiny. Next, I need to compute the square of the amplitude. So, okay, the boundary condition is to have an m and an m prime, yeah, right, this thing, and have an m and an m prime. That's at the edge of the universes. And then I'm supposed to do the path integral in gravity to fill this in. Well, one topology that you can have is you fill this in, and you try to run the shell from m to m prime, but that's not going to work. That's the same diagram as we had before, and it's going to give you a delta function plus corrections at a parametric control that I'm going to push to 0. However, now we have an additional geometry to consider. This is this one, where you take this boundary condition, and connect them this way. And this is sliced correctly. This is a wormhole between these two universes, which had shells m and m prime. So we're going to add that in. So this is a connected contribution. And there's some work to do here. And at the end of the day, what you wind up getting is this quantity. This is a delta function from this part. And then there are two pieces. So this is like the Gibbons-Hawking partition sum that we already discussed before. And this is like the Gibbons-Hawking partition sum of twice the inverse temperature. I'm just writing it that way because I don't want to write out these formulae for each one. So that's the object you get. And there's some squares essentially in the end because there are two horizons in the game to deal with. Okay, so that's the answer you get. You can similarly do higher moments. This picture is going to look really cryptic because there's a sheet of the geometry over here, there's a sheet of the geometry underneath, you're connecting them. So there's a certain amount of mental gymnastics you have to do to think about what these wormholes are, but it's not particularly difficult. You can just go ahead and do that. Half an hour of thought will give you these answers, and you get further, you can calculate all the actions, and you get a certain answer. Okay, so am I right to have 10 minutes? Good. So we've arrived actually at an oddity. And I'd like to discuss that oddity for a few minutes. So we've found that the overlap psi m prime for two shells with two different inertial masses behind the horizon is a delta function, essentially 0 if m is not equal to m prime, up to tiny corrections, which we're pushing to 0 by making m minus m prime large. But we've also found that the semi-classical approximation for the square of the amplitude is non-zero. Right? How is this even possible? Because this is a number, squares of numbers is supposed to be squares of numbers. Something seems wrong. So here's our proposal for how you should interpret this from a microscopic point of view. The idea is that the semi-classical Euclidean saddle points, they're an approximation to the exact answer, and they are averaging over microstates that vary in tiny Planck scale detail. So let me explain what I want to mean by this, right? So suppose I want to think about the Euclidean saddle point that's sitting over here off in the complex plane, right? It's as if, on the real line, imagine you were doing complex analysis, and there are a bunch of poles along the real line, and they're sort of concentrated in some way. And then you want to do a contour integral around some of those poles. But instead, you do a contour integral around some pole that's off in the Euclidean plane, and you do a little circle around that. Well, there are theorems in complex analysis that'll tell you how the integral around one of these things is related to the integral of the other of these things. And this is essentially a sort of Green's function kind of effect. And each little pole produces a little influence because the function is analytic at this other location along the complex plane. I think that something like that is going on with the Euclidean path integral for gravity. And I think that is a major goal for our field, to understand that clearly. Anyhow, in that view, the idea is all of the states that differ, that are essentially the same from a macroscopic point of view, right? All these, the same shell describes them, but have tiny Planck scale differences, in where you put the dust. The idea is that they vary with random phases relative to the kind of energy eigenstates that, maybe Strominger and Waffa, or maybe the fuzzball community is trying to write down. So that basically, a little bit like the ETH hypothesis, that the matrix element of a simple operator, like one of these dust shells here, in two energy eigenstates is some smooth part, possibly zero. This can be zero if the operator doesn't have a one-point function, times some other smooth part suppressed by the entropy, and times some erratic phases. So this is a natural hypothesis to make, because although our operator for making the dust looks kind of heavy, it's actually extremely simple. It's the same operator applied again and again and again. It's a simple operator in that sense, in a very complicated state. We're expecting the energy eigenstates, the true energy eigenstates of the system, to be very, very complicated, right? I mean, like the things that Emil talked about, things that were talked about in the fuzzball talks yesterday, things of this kind. And we know that gravity is chaotic in many respects, so it's very reasonable to expect that these little variations in the microscopic positions of the dust particles lead to erratic phases. So, all right, so that's the same statement again. So if the semi-classical saddle points that we are actually using to do the calculation, right, because we can't do the exact path integral, remember, right? If the semi-classical saddle points are giving a little bit of a coarse-grained average over these states, then you can just show that it's going to be the case that unless A equals B, this overlap will look like it vanishes. That's because of a phase cancellation between all the little things you're averaging over, whereas the square of it won't, because of, there's an A here and A here, and the phases cancel. And so you'll get something non-zero out of it. There's no mystery to it. You just had a bunch of stuff which had some random phases, and if you calculate this, you'll get zero, and if you calculate this, you won't. Right? There's no mystery to it. It's just that there are these chaotic aspects to the microscopic dynamics of gravity. There's no fundamental ensemble, nothing like that. It's just that you're calculating, if you do semi-classical calculations, it's an intrinsically slightly coarse-grained quantity that you compute. And this is the nature of that coarse grain, is the idea. Anyhow, going back to our problem, we want to calculate the trace of the resolvent of the ground matrix. So here's the trace of the resolvent. It's this power series. So this trace of G bar to the n are precisely the moments of the overlaps. I already told you how to compute them, right? Using the semi-classical approximation. You stick those in, you calculate a little bit, and you can find, using the standard ways of thinking about this, a recursion relation for the trace, which looks like this. I'm not doing the calculation for you. I'm setting out the steps, trying to show you that it's pedestrian, so that there's no magic here. And you do some recursion relation, you get that. And then there's a further sort of subtlety that you have to deal with. So strictly speaking, it's easiest to compute in gravity when you fix the temperature, right? So you're working the canonical ensemble because the circumference of the Euclidean section is the inverse temperature of the black hole. In the canonical, that's the canonical ensemble. In the canonical ensemble, of course, the states you construct have support and everything. They're just suppressed by e to the minus beta e. So we could deal with that and talk about the bulk, where the bulk of the support is. The usual relationship in canonical and microcanonical ensemble is that you fix the temperature, and you'll find a peak in where the support and the states is. We could do all of that, but an alternate way of proceeding is to just work, project everything to the microcanonical window. As per, pick your favorite statistical physics book, Patria, or whatever, Kurdar or something. You do that by taking your partition sum and projecting it into the microcanonical window. So you have to carry out the analog procedure, the Laplace transform that you have to do. The inverse Laplace transform that you need to do, you need to apply that systematically in this calculation. So we do that. And then at the end of that day, that's so that we don't find out, we want to find out how many states are supported at energy E. How many states at energy E are you including? And we don't want, right, you don't want the entire tail with tiny, tiny supports out to very high energies. Anyhow, you sum this up and you get some quadratic equation of this form. That I can definitely solve. And then you work out from it the density of eigenvalues. And you get something like this. There's a smooth part with support away from 0. I haven't written out the details here. And then you get this piece, which is the part of interest to us. So there's a delta function at lambda equals 0. Omega here is the dimension of the Gram matrix. And there's an e to the s. So s is going to be area over 4g Newton h bar. So you notice that because of the theta function here, if omega, the dimension of the Gram matrix, namely the size of the, how many, I put a certain number of states in my bag of dust shells. If you pick fewer than e to the s, there are no vanishing eigenvalues. So the rank of this matrix is the number of different dust shell states. That accords well with the idea that I make a shell of dust here, I make a shell of dust there, I make a tennis ball there. These are different states, right? Or at least they help you span different parts of the Hilbert space. However, if omega is bigger than e to the s, there are omega minus e to the s vanishing eigenvalues.
Bonjour à toutes et tous. Ceci est un message destiné aux électeurs de l'établissement Paris-Saclay. Nous vous informons que les élections professionnelles ont lieu actuellement jusqu'au mardi 13 juin à 12 h. Nous vous encourageons à participer à ces scrutins afin de déterminer vos représentants pour les 4 années à venir au sein des instances nationales. Nous vous rappelons que ces élections se déroulent par voie électronique. Le site de vote est désormais accessible sur Internet. Nous vous remercions de votre attention.
When I was in elementary and middle school, the principal would come on the radio once in a while and tell us stuff that we should do. I feel like that. Okay, so anyhow, all of this means that the rank of the matrix, if you pick a sufficiently large bag of these dust shells, is e to the s, where s is equal to area over 4g Newton. So we come to, oh, I need one more piece. So now you could say, why is this a complete basis? You have enough states here. So the argument for that is, first of all, the product of any operator, the OPEs of any operator, contain any other operator in a chaotic theory. In particular, the OPEs of any operator contain the stress tensor. So from the dual field theory point of view. And so from the bulk point of view, they contain the graviton. Put another way, if you had made a shell of dust out of some other particle, some other kind of particle, you'd find the same overlaps that we found. The same overlap integral would work out. They have the same overlaps because it's a gravity thing. Right? The overlap between these things is being mediated not by the particles splitting and joining one to the other, but rather by the gravitational path integral. So that is our argument for this actually being a basis for expanding any state in the theory. So the bottom line is that we would claim to have a universal accounting of black hole entropy in any theory with general relativity as a low energy limit. Okay, so I have, what, 3 minutes? According to my watch.
Yeah, we started a little late, so.
Wait, according to my watch, it's 10:59, so I do have 1 minute.
Yeah,
plus 2 more.
Yeah.
Right, I have 3 slides, these are my concluding slides anyway. So one comment, and we can go through this in detail separately, is what we'd really like to do is to work with collapsing black holes of the kind that happen astrophysically. The Penrose diagram for a collapsing black hole looks like this. This is r equals 0. This is null infinity, and here is my shell of matter or whatever. Here is the shell of matter falling in to make my black hole. I can examine what this geometry looks like on this slice, for example. Sigma is a space-like slice. So what do suppose we would try to explain the entropy of this thing with the kinds of dust shells that we would have. So here's an example of a dust shell. What this would wind up looking like is if you put in one of these dust shells, then in the past you would get a geometry that doesn't look like, you could, on this slice, you can have exactly the same exterior geometry. Well, you can have the same exterior geometry here too, but in the past, you see, you would also have this horizon and you'd have this singularity here. That doesn't look like this in the past. So you might say to me, why should I allow these kinds of dust states then as microstates of the black hole as seen by the observer at this time? Well, the answer to that is it's for the same reason that when you count the entropy of the gas in this room, you count states of gas where all the molecules are sitting in that corner. That doesn't happen very often, but you count them anyway. And that's because when you think about the total phase space that you're interacting with, if I bump the gas a little bit, I may move the gas molecules into a configuration where if I extrapolate it to the past counterfactually, they were actually in one corner of the room. But I don't care, right? Because I'm not back then. Right now, they contribute to the phase space effects of the geometry. So indeed, states like this ought to be counted as microstates of the black hole at this time, at least in as much as they contribute to how you interact with the black hole. That's statement one. Statement two, this I find very cool, is you can, amongst the space of states we look at, there's things with dust shells inside, 2 dust shells inside, etc. And the back reaction of these shells stretches the wormhole in each case and increases their volume. So you can make this as long as you want. So that tells you that very long wormholes should be understood in our setting as superpositions of short wormholes. This is a macroscopic, very macroscopic manifestation of quantum mechanics, right? And very strange. And it also tells you that volume cannot be a linear operator in quantum gravity and ADS-CFT. I think that's very interesting and something I want to continue thinking about. Another final point that I'll make is one interesting thing you can ask is, can you in any way detect these states? Is there any sign of them? That's akin to the kinds of questions being asked in the last few days at this meeting. So if you look at the density matrix you'd get on either the left or the right, the insertion of an operator in the construction of the state means that the density matrix is not precisely thermal. There's some deviation from thermal. However, if you do things like compute the expectation value of the Hamiltonian in the slightly deformed density matrix, you will find you get the same answer. It had to, because the exterior geometry is the same. You're getting the same masses, etc. Right? But there are some kind of soft deviations in these observables. The deviation is controlled in some level by how far away the shell is from the horizon. We discussed this yesterday, Emil, and most of these shells are quite far from the horizon. But there's some very infrared deviation, some observables of the other from what you would get in the thermal density matrix. And this is something that we've not understood fully yet. So let me finish. So that leads me to a question. Why can't we detect all these states from far away? That is, why does there appear to be a horizon? So the answer that I think I would like to give, and also is consistent with what Emil was talking about yesterday, is the answer is that the states exist but are protected from interference by their complexity in some sense from in the interior of the black hole. The ADS-CFT language and the dual field theory, you start out with a simple state with the application of these dust particles, with these operators, but it's going to evolve in time according to the chaotic dynamics of the theory into some exceedingly complicated state. And then probing what that state is, you can show is going to be algorithmically complex. It's a very difficult job. So to all intents and purposes, for almost anything you can possibly measure, it makes sense to draw a line and say, I can't see this thing. Right? So I think the horizon is an artifact of the semi-classical low complexity approximations that we normally make. I'm going to stop there.
Thanks so much for the very nice talk. We've got time for a couple questions.
I already asked almost this question, but is there any hope to extend this to rotating black holes?
Yeah, so that's something we've talked about and haven't done.
In that case, the outside geometry is not fixed by the symmetry. I mean, you can have black holes which are, geometries that are axisymmetric, which are not the ones. While for non-rotating black holes, the structured geometry is fixed by the condition of the mass.
Sure. So we haven't thought carefully enough about that for the following reason. It actually isn't for that reason. It's for the reason that if you take the Euclidean continuation of a rotating object, there's eyes in the places, and then there's saddle points. So someone knows how to do analytically continue rotating objects and do Euclidean path integrals with complex saddle points, but I don't. Right, so and my collaborators, we haven't done this before, so we need to sort of figure out how to do that, and then we will try to deal with these issues too, but we haven't.
So a quick question about the last part of the talk. So is it possible to say that whatever the CFT states are, they're generically expected to be some high descendant states? Is that something
high
that
descendant states?
Yes. The reason I'm saying this is because in CFT, at least in 2D CFT, you can compute or you can show when, for example, statements like ETH will hold. And there, generally speaking, it's because in 2D you can do these calculations. Their ETH kind of statements hold generally for high descendant states, not for primary states or not for.
Yes, I'm slightly confused. So I thought ETH in general held for basically simple operators and complex states. So
yes, but I'm talking about the states.
About those states.
Yeah, about the states. Yes, generally they're not primary states. So, for example, if you take a primary state, an ETH, especially the random part that you showed, not the diagonal part, the random part that you showed, may not show up if it's just some primary state or low-lying states for sure.
I think you're saying possibly that the typical black hole microstate, energy eigenstate,
yes,
should be a descendant.
Something like that. Yes, at least in 2D you can do this. In higher DCFTs, I'm not sure whether this can be done. So I was just wondering that whether in your construction there's some way of saying that these states are expected to be some descendants.
Well, not directly so, because what we're doing is we're applying the product of, let's say, some primary. There's a product of many primaries applied in some more or less symmetric way to the boundary, and then we're time evolving that for a long time. And these things are. Yeah, so I don't think I have a direct answer to your question.
Okay, and so just a very quick another thing. I mean, related to this, I have asked this question also before, but I was just wondering. I mean, is it possible to compute, let's say, for example, correlations of this random part that you propose in your ETH like form?
So that involves computing other of these diagrams, computing the variances and things like that. So actually, there's a calculation of the variance of some of this in Martin's paper, Martin Saciota's paper that preceded ours, but we have not spent any measure. That's an important thing to do, actually, to compute the variances and the fluctuations in these quantities, because we've computed mean quantities. We haven't done that yet. Certainly, totally doable. Right? I mean, these are just doing these sort of gravitational path integrals and these approximations and so on.
Okay, thanks.
But we haven't done it.
One last question, quick question.
Yeah, so I have a question about the overlaps. So basically, you're finding that the overlap. So you're calculating overlaps of classical geometries, essentially, which means coherent states. And then I would expect that coherent states typically don't have a zero overlap, right?
Yes.
So is that the exponential part that you're throwing away? Basically, that's the non-zero overlap between the classical states.
Yes, right. I mean, so
okay.
That's the thing that's being controlled by the mass difference between these things. So if I take the harmonic oscillator analogy, what we're doing here is we're taking the two harmonic oscillator, the two little coherent states, and moving them very, very far apart.
Good.
So that they're parametrically so I reduce their overlap.
Okay.
And then let gravity do what it needs to do.
Good. So then my follow-up is that something I remember from a long time ago from Papadonios Raju is that they say, look, when you do this in gravity, actually the fat tail overlap, right, which you're trying to make parametrically small, is much larger than you expect it to be. Is that something that you see or have any?
We certainly don't see that. We also haven't. If I understand your question correctly, then we haven't evaluated that. I think.
Right.
I think you're saying that suppose we make objects like this and try to move them far apart, they'll have more overlap than not. But let me finish. If they're making a statement about gravity, this is the calculation in gravity.
Well, but you're doing a saddle point. I mean, you're
Yeah.
making approximations, right? And so maybe the question is, are you maybe throwing away other saddles that?
Oh yeah. So that's a good question. Whether there are additional saddles is a good question, right? So that we do not have an answer to. We're of course taking the most symmetric saddle, etc. We have not done a careful analysis of additional saddles that may be here that increase the overlap
Exactly.
or something.
Exactly.
No, we have not. We have not analyzed those additional things. I gave a talk almost exactly 1 month ago at ICTS, and what do you know? A person named Raju asked essentially the same question. I wonder why. Yeah, but we haven't analyzed if there are additional saddle points that contribute. But what they're talking about is not this thing with the e to the m, because this effect is not gravity. This is a separate sort of field theory kind of thing that we're controlling. But we expect and hope we're taking the dominant effect here.
I think it's a good fodder for the coffee break. So let's thank Vijay again.
Thank you.
And we return what time exactly?
Let's try at 11:35 perhaps.
All right.